Okay, so this video is inspired by one Dan Jones has just posted on his Hookian channel, and a video, I can't remember when it was, but I'll put a link below to it from Lewis Matheson on the Physics Online. And it's basically about fuses, earth wires, other safety features within mains electricity. So I know on Dan's video, he showed a Lee cells kit that you can buy. I can't remember what he says the price is for it, but this is one I put together, and basically over time it sort of evolved, and and I think this now is it in its final arrangement. So the basic operation of this is you have your domestic plug wired up. There is a lid for it as well, but to be honest, the lid stays off most of the time. And the premise is that you have in the middle a kettle with a metal frame, and you have a person touching it. They're obviously touching the earth, so this lead down the bottom is the earth. And the idea is that when you switch on the plug, then our kettle turns on. My original version of this had a piece of nichrome wire between these two that glowed like the kettle would, showing it got hot. But I was finding that, that wire was causing problems. So it's a lot easier. This is just a 12-volt car bulb in the middle of it that shows operation. And the idea of this is when you turn on the fault, now, again, on some of the other kits I've seen, you have to physically touch a wire between the live and the outside, which is quite useful. It's quite a good way of showing that it's the live wire that touches the outside case. For mine, I went with a switch just because if you're teaching this, I feel like being able to be free from it and it just does its own thing means that you're not in the way of the students and enables you to discuss what happens. So the on switch here switches on the fault, so fault on. At the minute, the earth wire is off, so our earth wire is not connected. And we can see that without our earth wire connected, our fuse isn't melting and our person is conducting electricity across their heart, and the red there to show they've died, or at least got a shock. And then what we can do is we can talk, well, why didn't our fuse melt? And you talk about, well, you've still got quite a high resistance to the person, so the current, the extra current of the going through the person is not enough that melts our fuse. So now if we connect our earth wire, and I'll show you all the connections on the back in a minute, and we turn on our fault this time, what we will see is that we still get electrocuted because our fuse takes time to melt. And that once it's melted, it has rendered our device safe. But you could still see that current flow for quite a while, so you're still going to get quite a nasty shock whilst you're waiting for the fuse to melt. I know on the PTNC discussions online, there was a discussion recently about like the purpose of a fuse. Yeah, fuses don't stop people getting shocked. They stop overcurrenting devices and stop fires. And then we can turn it off, turn our fault back off, and then we reconnect our fuse. Here, I am just using a piece of, I believe it's iron wire, and it's just stored on the back. I can't remember the exact gauge of this wire, but with our wire, I'll just wrap this back on. So our wire is just wrapped back on, and you can see all I do is just wrap it around the terminals. If I cut a longer piece off, I can just use the same piece, keep moving it along, and with the fault turned off, our kettle turns back on again. So that shows the function of the fuse. I have also got in the back here some thermal cutoffs, some thermal MCBs. These are rated for 3 amps, which is just over what the normal operating current of this is. The only thing I would say is they do get times they do take too long to cool back down before you can untrip them. But also they still take quite a while to trip at first. If you are going to demo these, it's worthwhile doing it a few times because they do get quicker as the internals heat up, because these, I believe, use a bimetallic strip rather than electromagnets like a normal AC circuit breaker does. The other thing that's on this, and this is something that took a while to develop, was I wanted to show the function of an RCD, because obviously students need to have an appreciation of the differences between all three safety devices. So here I have a switch that turns on the RCD, and we have our test button, and we have a reset button for it. Now, obviously, if you know the basics of RCDs use magnetic fields and electromagnetic induction. This device is running off 12 volts DC. So you cannot use a normal RCD in this because you haven't got the alternating current to induce the alternating magnetic fields. So instead, what this device uses is an Arduino. I'll put a link to the code that is used in the description. But what this is doing is it's got two current sensors, and they're measuring the current in and the current out of the device. They're basically measuring the current in the live and the neutral wire. I've got a loose wire somewhere. And if the current in those two values is not the same, it will trip. So if I then turn on the fault, if I actually turn on the fault with the RCD on, let's try that again. Right, let's try that again. So this time we'll turn the RCD back on. RCD is on. If we turn the fault on, we will see that now our RCD trips almost immediately, meaning that we don't get a shock. And here, even if we hit the reset button, you can see that this will trip pretty much immediately, reducing any danger. And also you can talk that actually RCDs will work whether the earth wire is on or not. So here's our earth wire off, and our RCD still works when we have our fault. So you don't actually need an earth wire for an RCD. Right, on to how this works. So probably the thing that took the longest to work out was getting a power supply for it, because most benchtop power supplies, the current draw when you've got that fault is high enough that the power supply, quite often the trip on a power supply goes first before the fuse melts. So this is a 120 watt 12 volt power supply, switching power supply, designed for lighting, 12 volt lighting. So obviously 120 watts at 12 volts, it can supply 10 amps, no problems. And that is probably the hardest thing to do. So you've got your power supply in. On the back here, the power supply obviously goes through. If we have a look, this device is our RCD circuit. Here's our Arduino. And what I'll do is hopefully there's a circuit diagram coming up on the screen now, and I'll talk through our actual circuit here. This device, again, I was having problems with the Arduino browning out, basically, that when I was supplying this with 12 volts, the Arduino would brown out, so that means it wasn't getting the voltage it needed to work properly. So all I've got here is a 12 volts to USB converter. So it takes the 12 volts in from the power supply, converts it to 5 volts, 5 volts on the USB, and then I've plugged that USB in to our Arduino to power it. I just found this was much more reliable than trying to power the Arduino via its voltage import, or the 5 volts on the Arduino. Both of them I was finding that basically I was burning Arduinos out getting this to work. This is a much more fail-safe system. We have also got buried underneath here the relay for our RCD, and the red lights here in there, that is our two current sensors, one on the live, one on the neutral. Like I said, there'll be a circuit diagram. There's a circuit diagram on the screen now. So our power supply, our power comes in. This rail down the bottom is our earth, or our neutral rail. So our power comes in, goes to our current in, sensor through our current in sensor and into the back here of our plug socket. So there's our live on our plug socket. It obviously then comes up through our fuse, through our flex, into our crocodile clips, through our bulb, through our neutral, and then back. The neutral comes through. Then our neutral goes to our current out sensor before the current out sensor is then connected to our sort of earth bus, or our our neutral bus at the bottom. That shouldn't be there. That was some fixing I was doing earlier. Okay, in terms of you can also see we've got our earth wire then. So this is our earth wire in our flex connected to our earth wire here. Our earth wire comes out. Now I found I had to put, I think this is a 1.5 ohm resistor. I had to put a small resistor on the earth because basically that short circuit was just causing so many problems with power supplies and everything else that it was a lot easier. Just put a small resistance in that, just so that it kept the circuit going. So here's the back of the switch. And again, so our earth wire comes through the resistor and is connected directly to our earth, or our 0 voltage, our neutral bus down the bottom. Other connections then, this is our fault connection. So this lead comes out, goes through, comes up to our fault switch. And the other side of the fault switch is connected to the live wire. So this here is connected to the live wire. So this is connected onto the back of this. So that we've got our live wire is then being connected through the switch to the outside. Obviously you've got your connections with the LEDs and their in-series resistors. So I think what other connections there are on this. Yeah, our RCD, this is just powering the RCD, powering on our voltage controller, which powers our Arduino. And again, I'll hopefully post a circuit diagram. I'll put a circuit diagram of what's on the back. So yeah, hopefully that helps, and good luck building stuff. The gauge of the wire, again, I think I took this off Lewis's video. So if you watch Lewis's video, it'll tell you what gauge of wire this is approximately. I don't think it's written on the back. No, it's not. The iron wire, let's see if I can get it back. And then all I've got on the back here is just, storage. Quite messy, the back. There are instructions as well of how to use it. No, I don't think I can get that off to tell you what it is. I think the value's written on the other side. But yeah, just experiment. I think the best thing to do is, most schools I know of have a wire drawer. Just experiment to find out what gauge works best. Thin copper wire does work. It doesn't melt as quickly, it melts quicker than the iron wire. I also find that it doesn't melt as spectacularly, so the students can miss it a lot more easily. Thanks for watching. Hopefully that wasn't too long or boring, and good luck. If you have any questions, put them in the comments. I'll do my best to answer them.